Hello and welcome everyone. Thank you for joining us. My name is Serdar Kadıoğlu. I help Fidelity to build modern recommendation and optimization systems to enable digital native customer experiences. When applying machine learning models in the real world, I think we have all experienced that sometimes live experimentation takes forever. And this is exactly what this talk is about. Today, I'm going to show you how you can speed up your online experiments. Now you might ask, why does this even matter? Well, if you can boost exploration, what that means is you can reduce your opportunity cost, generate more learnings from your experiment, and achieve positive results faster. To speed up experimentation, I'm going to show you a multi-objective optimization framework. Further, I'll share insights based on our experience from building real-world applications in the AI Center at Fidelity Investment. Probably you're all very familiar with recommender systems because we all interact with them on a daily basis. They are widely employed in the industry, and personalization has become a billion-dollar business that continues to grow significantly year over year. The primary goal of these systems is to help us discover relevant content, such as movies to watch, articles to read, or products to buy. In return, this creates an enjoyable digital experience for us and drives positive outcomes. While recommender systems have become central to our daily lives, what you might not know is that it still remains a common challenge in the industry to create machine learning applications, especially when there is limited or no training data. This is often the case when we would like to launch a new customer experience or a new product that didn't exist before. In the most classical setting, we have a set of users and a set of items from which top K items are selected and shown to the user. Now notice one thing here. Who decides the universe of items that a recommender system should interact with? Surprisingly, this aspect is often neglected. So the central question I'd like to address in this talk is how to select the set of items when designing a new application. We need to be careful about the universe of items because item selection matters a lot. Here are main trade-offs that makes item selection an important problem to study. First of all, the more items we include, the longer the experimentation takes. This incurs unwanted cost in terms of poor customer experience and negative business impact due to missed opportunities. On the other hand, more items lead to more diversity, which is good for learning purposes. With the right mixture of items, we can cover more outcomes and reach out to a larger audience. Not only that, but keep in mind that these items do not come for free. With each item to add to my recommender system, there is an onboarding effort. This includes reviewing the item, publishing it, producing it, and at the end of the day, these items need to be part of some content management system. These are the direct consequences of not thinking about item selection. So all of this leads us to a single question. What is the right mix of items to start initial experimentation? I'd like to stress again that this is especially critical for new experiences with no historical data or no data that we can transfer from different applications. The solution to this question lies in a principled approach for item selection. And this is exactly what I'm going to talk about today. We formulate a new combinatorial optimization problem to generate optimized item selection and refer to this as the item selection problem, or ISP in short. The approach is based on tree building blocks and integrates techniques from discrete optimization, unsupervised clustering, and latent text embeddings. So, what am I trying to achieve with this talk? This talk will be successful if by the end of it, you're familiar with the item selection problem so that you can quickly evaluate whether it becomes relevant in your own applications and build a high-level intuition on how to approach the problem. So with that, here's our roadmap so that you have a mental picture for what's ahead of us. First, we will start with an illustrative example and present the problem definition. Next, I'll share a high-level system design to show where does this problem fit in the larger context of system architecture. Then, I'll present our multi-objective optimization approach and quantify its benefits on well-known data sets. Finally, I'd like to end on a broader vision for human-in-the-loop decision-making and discuss how we can empower our business partners. So let's dive in and start with an illustrative example to present the item selection problem. I'll also share a high-level system design on where does this problem fits in the bigger picture. To make the problem more concrete, let us consider a movie recommender system that all of us can relate to. In this setting, the items correspond to movie titles. In other applications, items could be articles, podcasts, products, or call to action messages, and so on. In this setting, we not only have a set of movie titles, but for each movie, we also have access to item metadata. For instance, we have a range of categories such as the title, story, genre, language, producer, stars of the movie, and so on. Each category will have its own label values. For example, a category like genre can have different labels such as drama, action, or a spy movie. This type of metadata exists for all items. I'm presenting this example so that in the back of your mind, you can map this setting to your own applications and decide what type of categories and labels are applicable in your case and what metadata you have available or you would need. Now, to be more precise, if we bring this together, here are the main ingredients of the item selection problem. A more formal description can be found in our papers. We have a set of items I, and what we are interested in is a subset of items S for experimentation. As we have seen in the example, there are different categories C, and within each category there are different labels L. Now we can use this metadata to create deep latent representations of item embeddings, taking advantage of GPUs. What could this representation look like? Well, the representation can come from NLP on text embeddings of movie titles or reviews, or it can be based on computer vision on images such as on movie cover art. Alternatively, it could be audio based such as movie soundtracks, or based on videos such as the film trailers. In that sense, our framework is pretty generic and can be applied in a wide range of applications. Given all of this, the goal of item selection problem is to find the minimum subset S that maximizes label coverage within each category and also maximizes the diversity of the selection in the embedding space. In other words, we are trying to find the smallest subset so that we can speed our experimentation, but also we want coverage and diversity guarantees. At this point, I'd like to take a step back and talk about where does ISP fit in the bigger picture of recommender system architecture. Now imagine we are launching a new product. We start by solving the ISP and get a subset of items to include in our experiments. Then we go ahead and run randomized experiments to collect training data. Using the collected data, we train recommendation models. In order to train these machine learning models, we can take advantage of GPUs and the state-of-the-art recommender models. Next, we use a warm start procedure to augment the set of trained models to also include additional items that were not included in the initial stage. Finally, we deploy these trained models and start generating personalized recommendations. At the inference stage, we can again take advantage of GPUs so that we reduce our scoring latency and achieve real near-time behavior. As time proceeds, the system generates more feedback data, which we can use to update our trained models, and the process continues. In this talk, our focus here is on solving the ISP and the warm start procedure. The other boxes are generic recommender system components, and we can exploit GPUs and best-in-class techniques from the state-of-the-art. Alright, in the previous section I told you about the item selection problem, why it matters and where does it fit. Next, let me show you how you can solve this problem. Our solution is based on a multi-objective optimization framework that uses cover formulations. I previously mentioned that ISP is subject to several trade-offs. The good news is these trade-offs lend themselves naturally to multiple goals in our optimization framework. So what are these goals? Number one, we would like to minimize the cardinality of the item universe. This would shorten the experimentation time window, reduce our opportunity cost induced by random experiments, and save us effort in content onboarding so that we can speed up our time to market. At the same time, we want to make sure that all labels are covered so that once we collect feedback data, we'll learn about different options. In parallel, we want to maximize item diversity in the embedding space. So for latent representations, we turn to text embeddings and use our open source TextVisor library for text featureization. The embedding comes from the text of the movie titles and their storyline. Let me add a quick side note here. If you feel confused with so many different options for pre-trained NLP models and embedding techniques, you should definitely check out TextVisor and our corresponding paper for an approach that presents a unified view. Now, let me present you the main steps involved in our algorithm. The solution approach consists of 3 main steps. In step number 1, to minimize the subset size, we use a cover formulation to select a subset of items that cover all predefined labels. This is a standard set covering approach that's commonly used in the discrete optimization community. However, this simple mapping from ISP to set covering does not take diversity into account. For that purpose, we turn to latent representation of items. And how do we do that? In step number 2, we change the loss function to also incorporate the diversity cost. In other words, we are interested in a subset of items that cover all the labels, but also far away from each other in the latent space to increase diversity. There is still one caveat here. We don't have any control on the size of the item universe. If you think about it from a business perspective, we probably have a good idea on how long we want to run an experiment. This is more of a business-driven decision than purely algorithm-driven. So in step number 3, we address this scenario where we can have a hard limit on the experimentation time. For example, I only have 6 weeks to run a live experiment. When that is the case, this last step shows us what should be the best selection within the boundaries. The 3 steps I just described can be captured with an elegant mathematical optimization formulation. In fact, this formulation gives us a provably optimal solution on how to guide experiments. Now, without going into the details of the math, let me give you the high-level intuition behind what's happening. What you're seeing in this plot is each little dot represents a movie, and we are looking at their distribution in the text embedding space. The solution, which is shown in the blue dots as the selection, is the minimum subset of items. These items are the most spread out from each other while still maintaining the guarantee that all labels are covered. The high-level idea here is to cover all labels with the least number of items while simultaneously keeping the selected items far from each other. As I showed you in the high-level system design, we can use items in our initial experiment. Not only that, but we can use these items to warm start the ones that we didn't consider yet, or completely new items that arrived recently. This is where the approach becomes extremely powerful. Our selection is diverse by design, so we can exploit this property for item-to-item similarity and employ warm starts. Alright, now that we have covered how the solution works, what remains to be seen is the benefits of the approach. The first and most important question is, what is the minimum number of items that cover all labels? And if I compare that selection with the original universe, how much speed up we can expect in the experimentation time? Another important question is, what is the sensitivity here? Can I trust this? We are operating in the latent embedding space, which remains undefined, so how much results would deviate depending on different design choices? In order to quantify the answer to these questions numerically, I'm going to show computational experiments on well-known benchmarks from MovieLens and Goodreads datasets for movie and book recommenders. Both of these benchmarks are well established in the community. I'll consider a small dataset with 1,000 items and a large dataset with 10,000 items. The goal is to cover all possible labels in several categories such as genre, producer, language, or even pairs of categories such as genre and language pair. These datasets consist 500 and 1,000 unique labels in the small and large benchmarks respectively. So this is what I'm trying to cover with the least amount of items. The first question we are interested in is how much reduction and speed up I can expect. It turns out for the small data set, 75% reduction is possible. So to put this into context, instead of experimenting with 1000 items, only a quarter of it is enough to start our experiment. What that means is my experimentation will be 4 times faster, and this is quite astonishing. For example, if you planned for a month, you can get initial results within a week instead. In the large dataset, the reductions are even more remarkable, up to 90%. That's an order of magnitude speed up. We are talking about a week instead of 2.5 months. Think about how much we can mitigate undesired customer experience or the opportunity cost for business KPIs. Now, you might of course be wondering, is this the only way to solve this problem and what other methods exist? And yes, certainly there are other ways to do this, anywhere from a randomized approach to a greedy heuristic or a clustering-based method. The result I just showed you significantly outperform these other alternatives. And the secret sauce here is in treating this problem as a multi-objective optimization and solve for conflicting criteria simultaneously. The second question is, can I trust these numbers? Are they robust enough? To quantify this, we will look at different text embeddings and compare unit coverage. That is, the net value that each item brings to the selection. Again, we are using our TextVisor library, which is built with GPUs in mind, which makes running these experiments pretty straightforward. The methods that I consider range from simple counting-based techniques like TF-IDF to serve as a baseline, as well as deep representations like word-to-vec, global vectors, and byte pair embeddings. What we find is, as shown in the higher unit coverage numbers, more sophisticated methods provide better latent representations. The good news is that the results of the baseline is not far from that either. And overall, the methods do not deviate from each other that much. The important realization here is conducting a principled item selection is more critical and more important than the particular choice of embedding space. So, to bring all of this to home, the main takeaway from this talk and my call to action for you is think about which items you really would like to include in your experiments. I showed you that multi-objective optimization can be an attractive approach that you might want to consider in your own applications. In the last part, let me conclude with a broader vision statement. The presentation so far assumed a completely automated approach, whereas in reality, this is a perfect example of human-in-the-loop decision making. The inclusion and exclusion of items might be subject to further criteria that might not be captured in our models. Or at the very least, when we are launching a new product, these choices require an explanation for our business partners. It's important to provide insights and shed light on how we are designing the experiments. For that purpose, we build tools for our business stakeholders that enables interaction with our algorithms. Here you can see the embedding space and the underlying network structure used in warm starts. If desired, we can override and roll back some of the algorithmic decisions, or even make manual selections upfront to seed the results with our immediate preferences. At this point, you might be wondering what is next and where can we go from here? At least 2 things come into mind, one in the short term and one for near future. I talked about item selection as one-time activity, but the problem remains relevant as recommender systems are running. Recommenders operate in a dynamic setting where items come and go constantly. And there's an interesting connection here between item selection and active learning. Our current research is focused on the integration of the two so that we can dynamically solve the ISP multiple times while the systems are running at scale. Now that's for near term. More broadly, in the future, these human-in-the-loop systems can play a significant role to help us define business strategy and product roadmap, to make suggestions on what items to consider next, even before they exist. So with that, let me conclude here with some references to related publications from our group, as well as links to our industry-strength open source software in diverse domains such as recommender systems, contextual multi-embeddeds, natural language processing, pattern mining, feature selection, and AI fairness and bias mitigation. These libraries are all open source, well tested and documented, so you can update them in your applications immediately. All of this is possible thanks to my amazing collaborators who helped me understand these topics and brought everything you have seen in this presentation to life. I hope you found this session useful, and thank you very much again for your time. If you would like to talk more about applications of machine learning, I'll be happy to connect.